We're going to talk now some more about general inner products. Let me start with an example. This is kind of a little bit of a summary from what we did last time. Consider the 2 by 2 symmetric matrix, 1, 2, 2, 2. Call that A. And let's use that to define an inner product, as usual. We define the inner product of V and W is V transpose AW. And for example, let's compute what the associated quadratic form is when evaluated on the vector 1, 0. So that is to say, that's the inner product of 1, 0 with itself. And so that's 1, 0, 1, 2, 2, 2 times 1, 0. And by the way, you can be a little bit sloppy about where you put the transpose. The point is that you need a row vector on this side and a column vector on this side. And so as long as you have the transpose on one side and not on the other, and you'll be okay. So anyway, so what is this? This is equal to 1, 2 times, or dot, 1, 0, which is 1. So this vector has length 1, which is nice. So let's let V be the vector 1, 0. And so the length of V is 1. So here's a question. I've done this kind of thing before. I'd like you to find a vector W which is orthogonal to it, such that V is perpendicular to W. Okay. And let me give a second part to the problem. And such that the length of W is equal to 1. That's the second part. So I'm going to pause now and let you pause. I should say I'm going to let you pause and work this out for yourself. So pause the video and come back when you've at least done the first part. Okay, what'd you get? Let's see. I'm trying to find a vector. Let's write W as the vector AB. And so I'm trying to find a vector such that this 1, 2, 2, 2 AB is equal to 0. That's the first part. And this says 1, 2 dot AB is equal to 0, which is to say A plus 2B is equal to 0, and which says that I could take A is equal to 1 and B is equal to minus a half. Okay, so that's W. 1 minus a half. That's the W satisfying the first condition. Okay, so let's do the and now. And let's try and find W whose length is equal to 1. So again, I'm going to let you pause the video and see if you can do that. Okay, what'd you get? Why not? You couldn't find such a W? Well, if you did find such a W, I suggest you go back and double check, because you shouldn't be able to. So let's see. What's the length of this? We found a vector which satisfies the first condition, and I just need to get the second condition. What's the length of this vector? The length of W, or the length squared, I should say, is 1 minus a half times this matrix 1, 2, 2, 2, 1 minus a half, and that's equal to 1 minus 1 is 0, and 2 minus 1 is 1, dot 1 minus a half is minus a half. That's interesting. So if it had come out to be 1, I would have been happy. It didn't, so let's see. How could I find a vector which works? Well, if you just draw yourself a little picture, what I'm saying is I found the vector, this is the vector 1, 0, and then this vector which is orthogonal to it in this inner form is some other vector w, and clearly all the vectors which are possible would have to be multiples of w. The only there's a line perpendicular to 1, 0, which is the line through w. So the only choice is you could modify w and replace it with c times w, where c is any constant. And what would that make the length be? Well, the length of c times w is the length of c, the absolute value of c times the length of w, and the length of w is minus a half, so you get minus 1/2 times the absolute value of c, and there's no way to make this equal to 1, because the absolute value of c is a positive number. So the answer is it's impossible. And why? Well, this is not a legitimate inner product. This right here tells you there's a vector of negative length. This w is less than 0, so this is not an inner, not an inner product according to our definition. And if you check the determinant of this matrix, this is getting a little crowded, but I'll just put it up here. Remember, what does positive definite mean? For it to be an inner product, this matrix has to be positive definite, which is that A, which is in this case is 1, has to be equal to greater than 0, and that's fine. But you also need the determinant is greater than 0, but the determinant is minus 2, and that's not allowed. Okay, well, that was meant mostly as a sort of refresher and a little exercise to remind you about some things. So one of the things that came up there was if I have a matrix A, which is 2 by 2, and it's of the form A symmetric, so it's A, B, B, C, then it's positive definite exactly when A is bigger than 0 and the determinant is bigger than 0. And what if A is bigger? Well, to talk about this, I want to remind you of something I said last time, and I said this a little fast at the end, so I'll say it again. So the setting is we have a vector space V, and we have an inner product, and if we choose a basis V1 through Vn, then we get a matrix A such that A1 V1 plus and so on times B1 V1 plus so on is the inner product of these things is the vector A1 through AN times A times the column vector B1 through Bn. And of course, for this to be reasonable, you have to have that A is symmetric and positive definite. And I also said last time, if you chose a different basis, W1 through Wn, you'd get some other matrix, I'll call it A prime, such that the same equation holds, except using this other basis, W1, W1, and then inner product with B1, W1 is equal to, well, you still have the same numbers here, A1 through AN, except I have to put a different matrix here, A prime, B1 through Bn. Now, why is it a different matrix? Well, this vector, which is this linear combination of the A's, and this vector, which is this linear combination of the B's, of the W's, even though they both have the same coefficients, the A's, since this involves V's and this involves W's, these two vectors are not equal. And similarly, these two vectors are not equal. And we're taking the inner product, and so obviously there's no reason for this inner product to be equal to this one, so it's obviously some different matrix A prime. And I mentioned last time that you can actually realize that A prime is equal to some change of basis matrix B A B transpose. And a key fact about this is, remember, I mentioned this last time, but I'm going to write it out. I said that A is symmetric. Well, A prime is supposed to be symmetric. And here's a helpful fact, that if A is symmetric and B is anything, then BA B transpose is symmetric, which is to say it's equal to its transpose. Right? So this says A is symmetric, and this says BA B transpose is symmetric. And why is that? Well, what is BA B transpose? Transpose. So remember, when you take the transpose of a matrix, you take the transpose of each of the terms, but you also switch the order. So you get B transpose transpose, A transpose B transpose. And taking the double transpose, you get the matrix back. And A is symmetric, so you can cross out this term, and you get BAB transpose. So in fact, that's correct. This matrix, when you take the transpose of it, you get itself back again. So that's good. So just pause and think about that for a second. You can use any B. It doesn't have to be symmetric or anything. You take this matrix A, you can conjugate it, or not conjugate, you can multiply on the left and right by like this, and you'll get a perfectly good symmetric matrix this way. And it's also true that A is positive definite if and only if A prime is positive definite. And why is that? Well, actually, I mean, you could do some kind of crazy calculation, but it's actually obvious, because A and A prime are both giving you the same inner product, just in different bases. Since they're both giving the same inner product, which I assumed was positive definite. So, of course, when I said inner product here, by assumption, this is positive definite. And what does it mean to be positive definite? It means that if you plug in any two vectors, VV, it's greater than or equal to 0. And, well, this is the same. Both of these have to do with this, these are two versions of the same inner product. So that's fine. This is true. Okay. All right, now check this out. So suppose let's use black. Suppose A is n by n, symmetric, and positive definite. Let's do the LU decomposition, or I'll say it in sort of the other way. You can multiply A on the left by a lower triangular matrix to make this upper triangular. Right? And remember, L is special lower triangular. L is ones down the diagonal and something down here and zeros above the diagonal. Now, of course, A is symmetric. If you multiply on the left by L, this is no longer symmetric. But if you take the same L and you stick it on the other side with the transpose, this is definitely symmetric. That's what I was saying on the previous page. Okay. And let's think about that for a second. So this L times A is some upper triangular matrix, A1 down to AN, 0 star. And then I'm multiplying by L transpose. So L transpose is 1s, 0, and something up here, because when you take the transpose of this matrix, it looks like this. And this is the product of two upper triangular matrices. So this is upper triangular. This is of the form, I'll call it B1 down to some Bn, 0 star. Now, I know what you're thinking, but didn't I say it was symmetric? I did. So this was LA, and this was L transpose, and this matrix is automatically symmetric. How can this matrix be symmetric? This has to be equal to 0, and in fact, LAL transpose is exactly B1 through Bn 0, 0. Isn't that neat? Okay, so what that says is that if A is any symmetric matrix, you can multiply on the left by some lower triangular L and on the right by L transpose to make it diagonal. And whether this matrix is positive definite, well, that's if and only if this new matrix is positive definite, because these are just, as I said, these are matrices of the same inner product with respect to a different basis. And we know how to tell whether this is positive definite. That's if and only if all the BIs are positive. So that gives a very nice result, theorem, or maybe you can call it an algorithm, depending on your state of mind. The theorem says that if A is an n by n symmetric matrix, then 1 L A L transpose is a diagonal matrix for some L lower triangular. L strictly lower triangular as usual, like this. And second of all, its A is positive definite if and only if the diagonal entries that you get this way are all greater than 0. So that's an algorithm for testing whether an n by n matrix is positive definite or not. Apply this algorithm, make it into a diagonal matrix, and check whether all of the entries are positive. All right, I'd like to make another comment about this algorithm. Notice, suppose, let me just do the 2 by 2 case because it hardly matters. Suppose I had a matrix which I'd applied this algorithm to, say, and I got B1, 0, 0, B2. Now, I said that I'm allowed to multiply on the left by a matrix and on the right by the transpose of that matrix. And, I mean, before I was saying that this matrix, I got to this point by using a strictly lower triangular matrix. But I'm allowed, it doesn't have to be, and in particular, I could take B to be diagonal. So B could be alpha beta down the diagonal. And if you use that, then this becomes alpha 0, 0 beta B1, B2. And then the transpose, well, it transposes itself. And what you get is alpha squared B1, 0, 0, beta squared B2. All right, so this is a kind of a significant formula. The fact is that you can scale these numbers here by squares, and that is to say by any positive number. Alpha squared is positive. So I'll state the general result here. If A is of the form B1 through Bn, then by choosing a new basis, alpha 1 V1 through alpha n Vn, you get to a new matrix A prime, which is alpha 1 squared B1 down through alpha n squared Bn. And let's see, what's the point here? So alpha 1 squared is some positive number. All of these, so you're allowed to scale by some positive number. And so you could arrange by taking alpha I to be the square root of Bi, you could actually make these all come out to 1. So that's really an important theorem, which I'm going to revisit later in a slightly different way. If A, well, excuse me, if you have an inner product, then you can choose basis V1 through Vn such that, so remember, when you choose the basis, that determines the matrix of the form. and a different basis gives you a different matrix. And if you're smart about the way you choose the matrix, then the matrix that you of the form is the identity, which is to say 1 is on the diagonal of size n and 0 everywhere else. A word about this. Another way to say what I just said is the following. So we have our n by n symmetric matrix. And it's also positive definite. The Cholesky factorization is the following. It's you write A is equal to M times M transpose. Where M is lower triangular with positive entries on the diagonal. So that is to say M is equal to square root of d1 square root of dn star 0, where these are the square roots of the diagonal, the square roots of the pivots, as they say in the book, or the diagonal entries after you've diagonalized it. And so then M transpose is d1 down to dn and zeros everywhere else. And we basically just proved that every such A has a Cholesky factorization. Whoops, a Cholesky factorization. Okay, I'll stop there and I'll see you in class tomorrow.